In this lecture we're gonna discuss AVR addressing modes and some directives. So first we're gonna start with some assembler directives. These directives helps the assembler to or help us in making the code more readable, and also saves some computations. For example, assume you have a variable which we define using dot equal 50 and beta equal 40. We can do something like this: LDI R23 comma alpha. This places in R23 the value 50. So alpha acts like a shortcut for 50. So whenever we see alpha, the assembler will automatically substitute 50 instead of alpha. Now we can do something even more powerful. We can do something like this. We can have some computations. For example, beta times 2, this is gonna be plus 9. So what happens here is that R23 will be 50 minus 40 times 2 plus 9, which is equal to 29. So we can see here that we can do some shortcuts. We also can do something with binary operations. We can do something like this. Let's define 3 variables. So now we can do something with operations, with logical operations. For example, C1 and C2 or C3. So what happens here is that R21 will be 0x10 and 0x50 or 0x04 should be equal to 0x14. So we AND those two bitwise and then we OR them with 4, so we have 14. We can also do some shift operations. The way we do it is simple. Also we use the C-like operations. For example, let's say 0. We can do something like this, and this shifts the whole constant one step to the left. So now we have R16 is equal 1 0 0. Okay, so these are some of the directives that we can use. Also, if we discuss the status register, we have the library m328def.inc, which includes some of the definitions, and these definitions are as follows: sreg underscore c, which is equal to 0. This means this is bit 0. If we have sreg, the carry bit is located in 0. If we look at the 0 bit, will be 1. This means at bit number 1 we have 3 bit. So and this continues to dot equal the last bit, which is sreg I, which is equal 7. Okay, this is bit number 7. Now instead of actually using, we can actually use these bits individually, as we will see at the end of this lecture. Also, we can do we can directly use it as an IO. We can so here, if we do out sreg R20, what we're doing here is setting C and C bits in sreg. So sreg acts like a normal IO registers. We also have shortcuts for ports. For example, we know that port B and C and D, of course, all of them like this, goes from bit 0 to bit 7. This will be called PB0. This is PB1, and this goes all the way to PB7. So let's say I want to set bits 0 and 1 of port B. I can do it easily using the directives. So I can do something like this: 1 shifted PB 1 or 1 shifted PB 0. So what this does is actually PB1 is equal to 1 and this is equal to 0. Okay, these are just the pin numbers. Okay, so here when we have 1 shifted 0 is going to be 1, so this will be equal to, and this is 1 shifted 1, which will be equal to 1 0. So R20 will be equal to this, or this will be 1 1. So in this case we set bit 0 and bit 1 using the assembler directives. And if I ask you to set bits 3, 4 and 5 of port B, it will be easy. Of course here we need to have out port B R20. Okay, so here we have LDI, same method, but this time we use PB3 shifted PB4 or 1 shifted PB5, and then out port B, R20. So what will be the value of R20? This will be, of course, this is PB0, PB1, PB2, 3, 4, 5, then 2 zeros. Okay, so this is a very handy method in order to actually save some values or set some bits in an IO register. We shift gears to addressing modes. So when we talk about addressing modes, we have seen before some addressing techniques. For example, when we say LDI R19 0x25 and then sub I, for example, R19 0x6. Here we have a single register addressing, and here we mean by the RD, which is the destination. So we have also 2 register addressing, which is when we do add, for example, R20 with R23. Here we are doing R20 equal R20 plus R23. We're using 2 registers as addressing, where we know the address of R20 and the address of R23. We also have direct addressing, which we use with LDI. For example, we do LDI or LDS R19 0x560. In this case, we're doing memory or SRAM of 0x560 will be equal to R19. So here we're doing a direct approach. And we've all seen these techniques in previous lectures. However, what we want to explain now is the indirect addressing mode, which is the topic of this lecture. Okay, with the indirect addressing mode, we're going to explain it as follows. So usually we place values in SRAM as follows. We're using LDS. This is the direct approach. But what if I have an array of values? Shall I do it one by one? This will be very tedious. Assume you have an array of 5 elements. So we have, for example, 0, 1, 2, 3, 4, and we have here values like 8, 7, 6, 2, 1, and we want to place those values in SRAM because, well, we could have placed them in register in the GPRs, but what if we have an array of 20 elements or 100 elements? So first we're going to take the example of having just 5 elements. So here we want something like this. So how can we have arrays inside the SRAM? Okay, so we know that typically what we do is to define an array. We say we need an array of 5. Okay, we know for a fact that A holds the address of the first element. In this case, let's say this is at 0x100. Okay, this is the value. So A will be equal 0x100. And if I want to access the first element, I say A of 0 is equal 8. This translates to A plus 0. The content will be equal to 8. The second element, A of 1, will be equal 7. This translates to A plus 1 equal, what's the value? 7. So what's A plus 1? This is 0x101. So we see the index gets added to the value, to the address that's in A. So let's say we want A of 4 is equal to 1. This means A plus 4 is equal to 1. So we have, this is 0x104. It has 1. So it will be nice if we have a way to access these values in SRAM in a similar manner, where we can control an index going through each of these values. And AVR offers this functionality using pointers. So a pointer is just an address in memory. Okay, so AVR has 3 pointers. They are called X, Y, and Z. Okay, and as we know, pointers are addresses. Okay, they are used as addresses. So we know that the pointer address in SRAM. So we know, or in the whole memory, doesn't matter. So if we have 0x0100, we need 16 bits. So this means we need 2 registers to hold this value. So the X register has R26 and R27 for this to hold the value of X, and we have R28 and R29, and this one will be R30 and R31. So if I do a table like this, we have X, it's taking 16 bits. It goes from, this is X low and this is X high, this is the low byte, and this is going all the way to 15, and this will be R26 and this is R27. Same thing for Y. We have Y low and Y high, and this will be R29 and R28. Same thing for the third pointer, which we call ZL and Z high, and we have R30 and R31. So these 3 pointers, we can use them conveniently to have a value that can be a way to have arrays. So let's work with the first instruction, which uses these pointers. So before we start with a pointer, we need to load it with an address. As we said, let's use pointer X. So X should point somewhere here. Let's say 0x130. Okay. So first step, we need to load the pointer, which is the address, with its value. So an example, let's make X points to location 0x0130. So what we do is, first we say LDI. Conveniently we can use XL instead of using the direct register, just to know that we are using pointers. So the low byte will be XL and this will be X high, and LDI XH will be 0x01. So now I have X pointing here. Okay, and remember these are registers R26 and R27. So now, in order to read from X, from the memory, usually I used LDS, but in this case I'm going to use a special instruction called LD. I'm going to say, okay, LD R18X. And what this translates to is that, alright, place in R18 the content of SRAM at X. What's X? Of 0x130. So here we did the same thing that we have done before. However, instead of using LDS, we used LD. So with LD, takes a register and a pointer, and what it does is place in RD the value pointed by X in RAM. This is RAM. Okay, so any place in RAM, I give a value for X and I can read from it. Okay, I can do something else. Let's say I can do another example, LDI ZL 0x9F, LDI ZH 0x13, and then I say, okay, ST ZR23. And in this case, what I'm trying to do is say okay, place in the SRAM of Z the value in R23, and in this case SRAM will be at the address 0x139F, whatever R23. So this will be something like this. and here 0x139f, and z will be pointing here. So you see we can load 3 pointers at the same time, x, y, and z, and we can actually use them to indirectly reference the values here. Why it's indirect? Because we're giving it in x instead of using LDS as a direct approach. So let's say I want to store an array, okay? Let's say array of all ones, or let's say I want to clear an array of 5. So here you can see that x now, the difference between LD and LDS is that x now is a variable which I can add to it and subtract from it. So let's do an example. I want to copy the value 0x55 to location 0x140 to 0x144. So what do I mean by this? So first I need, let's say this is location 0x140, and I'm gonna go all the way to 0x144. So I want to place in each one of these 0x55. So I want to place 0x55 in all of these places. So as if I have an array from 0 to 4, each with 0x55. Okay, so to do this, first I need to set up my pointer. So let's use x. So first I know that the memory I want to point to is 0x140. So I need to place x pointing to 0x140. So I say, okay, xl will be LDI xl 0x40, and then LDI xh 0x01, and then I will say, okay, I need to do this. How many values are from 140 to 144? These are 5 items. Okay, so I need to do a loop for 5, and then I need the value that I need to save in each register. Then I'm gonna loop. I'm gonna say store in x the value R17. So what this does is saying that, okay, this is the RAM of x will be equal 0x55. This is R17, and this is now 0x140. So now I will have to go to the second step. So I increment x low, and this is saying x low is equal x low plus 1. In this case it will be 141, and then I will decrement R16. So this is, which will be equal, in this case, 6 minus 1 equal 5, and then I'm gonna branch not equal loop, and this does it. So what I'm doing here is that at the first iteration I place it 0x55 at the value pointed by x. It was 140, then it will be 141. So the second time I'm gonna loop into this, so the second time I loop with it, instead of 140 I will have 141. So now I'm placing 55 in 145, and 5 becomes 4, and this will keep on going until I reach the value 0, and this will reach the value, well, 0x144, and this is fixed, so I can place 55 inside of x. However, I have an issue here. The issue is that this is doing an 8-bit addition. What if I have values that needs x high to be increased? What if the address was, let's say 0x1f, let's say e? So the first time it will be 1ff, the second time should be 200. If I write my program this way, this will not work. I need to do a 16-bit addition for this to work. However, we have some nice directives that we can go with without doing the 16-bit addition. So we have something like, so we know that ld rn comma x, this will load rn will be equal ram of x. Now I have a nice directive that if I place this sign here, this is called loading after, this is auto incrementing. So after loading the location by x, so what it does, this is first we do rn equal ram of x, and 2 it does x is equal x plus 1, and this is done in 16-bit addition. So I don't have to worry about the carry. Also I have a pre-decrement, this is post-increment. So if I do something like rn minus x, so what this does, let me put a line here. First it says x is equal x minus 1, and 2 we have rn equal ram of x. You see here, this is post increment. So we're doing the operation first and then we're incrementing. This is pre-decrement. Okay. Of course, this works for x, y, and z, all of them. So we have post increment and post and pre-decrement. So let's say I want to rewrite this code using these values. Of course, for LD I can do also ST, the same way it works. So I can do also ST, and in this case we have x comma rn, and we have st x plus comma rn, and we have st here minus x comma rn. Okay, we can use the same way, and we can do that. We can do it also. So if I want to rewrite this code to use the auto increment feature, okay, so first of course I need to, this will be the same, I'm just going to change the loop. So instead of using x, I will do st x plus r17, and no need for this, I can take it out, and we do decrement r16 and branch not equal loop. So in this case I will do, so when we see x plus, what we do first is, okay, I'm going to say ram of 0x140 is equal 0x55, and then I'm going to do 0x, well, let's say x is equal to 0x140 plus 1, and this is a 16-bit addition. Okay, and this will be done 5 times. So this is a very nice way to use this feature. Take an example to furthermore elaborate the idea of auto increment and the idea of pointers. So let's say I have 10 elements in 0x130. Okay, so this is element number 0 to This is 0x139. This is element number 9. These are 10 elements. I want to copy them one by one to 0x160. So this should go into this part. The second one should go into the second, and so forth. So I need to, so if you have the here 5, 6, I need to have then here in this case 5 and 6 all the way to 0x169. So I need to do this. So first I have two arrays here from 130 to 139 and from 161 to 169. So here I need to use two pointers. So I'm gonna say this is X and this is Y. So as a rule, the more arrays, you only can have 3 arrays because you only have 3 pointers to be used at a time. I can have an array and then finish using with it and then reuse the pointer. But when we have multiple arrays, we can have a maximum of 3 arrays simultaneously. However, here we only have 2 arrays. So first, let us, whenever we have problems like this, we first set up the pointers. So first, I'm gonna set up XL. I'm gonna say, okay, LDI XL 0x30, LDI XH 0x01, and then LDI YL 0x60, LDI XL 0x01. So this is the first step. Now I need to place the counter. We have LDI R16 10, or we can put 0x0A, and we need to do the loop. So with the loop, first I need to read this value. For this to get copied, I'm gonna write in different color. So I'm gonna first read this, place it in, let's say, R17, and then store it. So this will happen with an LD instruction, and this will happen in an ST instruction. There is always a mandatory passage to go to the GPR when going from one location to another. We cannot just copy it directly. We have to go through the GPR. So first, we're gonna load. So we're gonna use the post increment. Let's say this is R17. Come on, X plus. And now it's in R17. We're gonna store it. Let's say this is 1. So this is 1. And then store the value of. So we're gonna use post increment store also, and this will be R17. And this is 2. So 1 brought this value into 130, and it incremented, and X now is pointing in 131, and Y will be pointing to 161 now after these two operations happens. And then we decrement our pointer, our counter for the loop, and branch not equal loop. So in this case, each iteration, the 5 will be in R17 after doing LD. So here I'm saying if I have those values, I'm saying here, okay, R17 equal 5, and then I'm saying X is equal 0x131, and then here I'm saying, okay, RAM of 0x160 is equal what's in R17 5, and then I'm saying Y is equal 161, and this will happen 10 times until I reach 169, and this will become 0, and I will exit my loop. So this is a clear explanation of how to use pointers and arrays in AVR. They are very important to be in our usual programs. They are crucial, and it's very useful to know them. In the beginning of this lecture that it is very important to address bits. So previously we saw some IO instructions such as CBI, SBI, SBIC, and SBIS. This all works only on I/O registers. But what if we have a GPR? So we have similar instructions for GPR, and they are SBR, CBR, of course, and this takes a register destination and the constant, and here we have also another with a constant. Here we set the bits, and this is clear the bits. However, these have different functionalities from those which takes just the bit location. So here with CBR, what we do is we set bits indicated in K, and here we clear bits indicated in K, where K is an 8-bit constant. So how does this work? So let's say I want to set, or let's give an example. Let's say R17 0B, and let's say 0 1 0 1 1 0 0 1. Okay, and then I will say SBR R, let's say 18, or let's say R17 with 0B 0 1 1 0 0 1 0 0. So what happens here? So first, R17 is equal this value. So this bit number 0 1 2 3 4 5 6 7. What we're trying to do here is that we want to set, this is also 0 1 2 3 4 5 6 7. So what we're asking is set bit 6 5 and 2. So we'd look at here, this is bit 2 is 0, so this will become, we leave everything the same. 3 same, 4 the same, 5 is 0, so now it's 1, 6 is 1, and so it's no need for setting it, and we will have 0. So SBR checks the bit locations where we have ones, and it sets the location indicated by the constant supplied to SBR. As we see here, we have bit 2, so we will set bit 2, bit 5, and bit 6, and this is what happened. This is bit 6, this is bit 5, and this is bit 2. So let's say we want to try the same thing but with CBR, clearing the bits. So let's take the example now with CBR example. So now let's say we have LDI R17, the same value, and CBR R17. Now I'm going to give it also the same constant. So as we said, this is 0 1 2 3 4 5 6 7. Now instead of setting, I'm going to clear them. So this is R17. Now 0 1 2 3 4 5 6 7. So now I need to clear bit 2. So this will be cleared because it's already cleared. Now I'm gonna look, 3 and 4 are the same, so I'm gonna leave them as they are. Now I need to clear 5 and 6. So this will stay cleared, and this will stay, then this will also be cleared. Now we have R17 equal like this. These all stay the same. So we see that we cleared these bits and these bits, which are indicated by 2 and 6 and 5, and we can give whatever constants we have. Now with checking for bits, so these are CBR and CB and SBR. For checking for bit value and GPR, we can use SBRS, and it works in similar way as SBIS, and it takes a register and a bit number. So if bit location B equal 1, skip next instruction. So in this case, let's say we have LDI R17, it will be 2, 3, 4, 5, 6, okay, and we have here also 0 here, and these are 8 bits. We can do SBRS and say okay, R17, 3. So we place 2 instructions under it. So I can ask you now, given this program, what's let's put that 20 here. What's the value of R20 after I execute this program? So first of all, I need to check. So I placed in R17 this value. Then I said, okay, if the bit location number 3 is 1, I'm gonna skip. So let's check what is bit location number 3. So this is 0, this is 1, this is 2, this is 3. So this is the bit location I'm looking for. So is it 1? Yes, it is 1. So I'm gonna skip it. Same way as SBIS. So this means R20 will be loaded with 0x30 and not 20. So SBRS, it checks if a bit is equal to 1 and it skips it accordingly. And remember, this works for GPRs. We have for IOs, we have SBIS. Similar manner, SBRC works similar to SBIC, but in this case it is for GPRs, also takes RD and B. Test if bit B in RD is clear and skips next instruction if true. So let's take this problem again. We have R16 0B1 and we say SBRC R16. If we place here 3 and then LDI R20 0x55, LDI R20 0x30, and I ask you, what's the outcome of R20? So if we check, this is 0, 1, 2, 3. So is it clear? No, it's not clear. So this means R20 will be equal 0x55. So this will go and execute this one. However, if we change the problem a little bit and say, okay, instead of placing 3, I'm gonna, let's say this is 1. I'm gonna place 2. So this is the second case. So what's in R20? So if 2, I look at 0, 1, 2, this means I mean this bit, then it is clear, and in this case, after changing the program to 2, R20 will be 0x30. So in the first case, when it was 3, and this is when it was 2. So when R16 was tested for bit number 3, I say this is bit number, okay? When it was tested for bit number 3, the test failed. No skipping. However, in the second case, test was true, skip, next instruction. So these are very useful when we want to check individual bits inside a location and a GPR, and test accordingly the flow of our program. And this concludes this lecture about indirect addressing and bit manipulation.